slide on the PowerPoint, and I asked you guys to complete the right side, which I posted a discussion forum on Moodle in reference to that. So make sure that you do that if you haven't done it. So this pertained to solubility rules, and so we're going to use those solubility rules. So you'll want to have the solubility rules that were provided to you in the handout or the one that we were looking at here. So either one will work fine for what we're going to do today. So we're getting into chemical reactions, and there's a few different types of reactions that we have to look at. Now, when you look at the things I should have handed out, and I'm not sure that it's on there on the handout that I posted on Moodle, but there are several different types of reactions, okay? And that's where I want to get to right here. So the different types of reactions are going to be, and I'm just going to abbreviate reactions as RXN. So the first one would be synthesis. A generic equation for that is A plus B yields AB. And we'll look at a couple examples for that in just a minute. A second example would be decomposition. And decomposition is the opposite of synthesis, where it breaks down, decomposing. And then there's a third type here. All right, the third type is combustion. All right, so combustion is where you take a hydrocarbon, CXHY, so it has carbon and hydrogen. You react it with oxygen, and it forms CO2 plus water. Y'all might remember balancing these equations previously. So combustion's always going to be reactions with oxygen gas. Just keep that in the back of your head. So anytime you have oxygen gas, it's going to be a combustion, but typically we look at hydrocarbons reacting with oxygen. So a good example with this would be CH4 reacting with oxygen gas to produce CO2 plus H2O. And so to balance that equation out, you basically need to put a 2 there and a 2 here. All right. So this is just a quick example of a combustion. Now for synthesis and decomposition, I'm going to give you an example here. So for synthesis, let's see here. A good example for synthesis would be where you're reacting titanium with chlorine gas to produce titanium tetrachloride. All these are gases. So this is an example where you have A plus B yields AB. Now decomposition is the opposite. So a good example for that would be where you take titanium dioxide, you heat it up, so the universal symbol for heating is a triangle, and it breaks down to titanium plus oxygen gas. So that's another example of decomposition. Now, a good and better example is something that you're used to doing and seeing would be a soda bottle. Okay, in their soda bottle, you have carbonic acid. Carbonic acid has a formula of H2CO3. And what happens to soft drinks as you leave them open? They go flat. And what happens here is the carbonic acid breaks down to water and releases that in the form of CO2 gas. So this would be an example of AB yielding A plus B. And so there are 3 different types of decomposition reactions that you need to know. All right, if you look at the things I should know handouts on the bottom left-hand side, this is one of those. Another one would be NH4OH breaking down to form H2O plus NH3 gas. So put a star beside these two. Those two are two that you are going to want to make sure you either memorize or have on a flashcard, because those are things that you're going to see show up in the near future. All right. So there's a third one, but I'm not going to discuss that one too much because we don't see that one very often. These you're more likely to come across. In fact, y'all do come across them every time you drink a soft drink, or every time you clean a window with Windex, or use ammonia to clean whatever you're cleaning with it. So these are just examples of decomposition reactions. Synthesis is where you take 2 things combined to one. Another example for synthesis is where you take sodium plus chlorine to produce sodium chloride. And this is solid, this is a gas, and this forms 2 NaCl. So that's another example of a synthesis reaction. Now, where it really gets to being picky is whenever we get into the next 2 types of reactions. Now, so remember we talked about synthesis, decomposition, and combustion. So there's 2 other types of reactions. There's double replacement, which is called metathesis, and then there is single replacement. Now, double replacement reactions is a pretty large category, and that particular category has 3 different types of double replacement reactions. And so we are going to look at that first. The single replacement reactions, we will look at that towards the end, and we may not get to that today. So I don't think we will get to that today, but we will focus on the double replacement reactions. Now, what I'll do here is kind of break that down for you. So the 4th type is double replacement. And if you look at your resource packet that's on Moodle, there's a page that defines all these different types of reactions. It goes into more detail than what your things I should know handout goes into. So use that chemistry resource packet to your advantage. Now, there are different types of double replacement. There's precipitation. There is neutralization. And then the third one is gas forming reactions. All right. So those are the 3 different types of double replacement reactions that we're going to look at. Now, in each case, your double replacement reactions are going to be the same. So you're going to form AD plus CB. So A always goes to D and C goes to B. All right. And one thing that you want to make a note of is that when you write these products out, the whole point of what we're doing right now is to predict the products of a reaction. Okay. And when you write these products out, you got to be really careful in the order that you write them in. So remember that your metal always goes first, and then you write your non-metal. Also, pay attention to the charges of the metal and non-metal. Because what you're going to have to do here is you're going to have to write correct formulas. This is something you really need to be used to and comfortable with at this point in time. You don't need to be trying to relearn stuff that we learned, 6 weeks ago. This is something that you should have in your back pocket. All right. So if you don't, you got some work to do tonight. And so, again, all these double replacement reactions work under the same generic equation. Now, looking at precipitation reactions. So what we observed in this beaker, just looking at the picture here, all right, we have two solutions, okay? You have, in the top beaker, you have this solution that has no color, and the bottom beaker, the same thing. Now, once they drop the solution from the top beaker, you see all this yellow stuff that's formed. All this yellow stuff is called a precipitate. And what a precipitate is a solid that is formed due to an insoluble product. All right. So we're going to underline the word insoluble because that ties right back into the solubility rules that we just looked at. All right. So again, when you look at a reaction and it forms this solid is known as a precipitate, and that all drives right back to what we were looking at earlier with the solubility rules. Now, keep in mind that we're still working with this general roadmap. This is kind of what we're looking at. So it's a generic reaction. So one of these here are going to be insoluble. The question is which one? So to answer this question, what we have to do is we have to go back to the solubility rules. All right. So are there any questions on that? And I don't know if you guys can hear me or what's going on because nobody's saying a word today, but can y'all hear me fine?
Yeah, I can hear you.
All right. So we'll look at an example here. All right. So metathesis just means from the Greek word that is to transpose. So you're just switching places, exchanging ions, and then when you make that exchange, that's when the reaction happens. Now, it doesn't always happen. It does happen when you have compounds that are insoluble. So as we look at this first example here, all right, we have silver nitrate reacting with potassium chloride. And so you have AB plus CD. Now, as we start to predict these products, this is the thing you use, okay? You understand that A goes to D, and then C goes to B. So that's the thing, is you got it. So this is the part where this is not given to you. What you're given is silver nitrate reacts with potassium chloride, predict the products, and then determine which of the products are insoluble. All right. So the AG goes to Cl. Now AG, keep in mind, AG is +1, NO3 is -1. This all comes from just learning this. Potassium is +1 and Cl is -1. So when you come over here and you look, you got Ag, which is +1, and Cl, which is -1. Perfect. We don't have to do anything because they're balanced by their charges. Now, the second compound here that's going to be produced is the potassium reacting with the nitrate. So you have KNO3. Now, make sure that the charges are balanced. Potassium is +1, nitrate is -1. So the charges are balanced. So we don't need to do anything else to the formula. Perfect. Second thing we do is we check to make sure we have equal number of atoms on both sides. So there's one silver on both sides, one Cl, one potassium, and one NO3. So the equation is balanced, all right? So we have a balanced equation now. Check. Second thing we're going to do after we balance the equation is now look at the solubility rules, okay? So we're going to go back to the solubility rules. So we go back to the solubility rules, all right? And we look at AgCl. Okay, so what we need to do is figure out, is AgCl a solid or is it soluble? So in other words, is it insoluble or is it soluble? So go back and look at the chloride ion. So this is found in the soluble category. And let's look at the exceptions. So the exceptions are silver, mercury, or lead. And so I see that my silver here is one of the exceptions, so that makes this compound insoluble. So we write an S. So remember, the S stands for solid. All insoluble compounds form solids in solution. So we need to make sure we indicate that as a solid. Now, all nitrates are soluble, so that means that the other one is aqueous. So from this reaction, what we just determined was that we have AgCl solid plus KNO3, which is aqueous. So AgCl is your solid, so AgCl is your precipitate for that reaction. Any questions on that? All right, so let's go back to this slide. Let's talk about this reaction here, okay? So in this reaction, what I'm going to do is we're going to work it out. I want us to see what this yellow precipitate is. Yeah, that yellow precipitate is very prominent. So we have lead, 2 nitrate, aqueous. So in this particular one, we have PbNO3. Now in the top one, we have potassium iodide. So potassium iodide is being poured into the solution. So that's our second reactant. Now, just like we've seen before, we need to establish the charges, and then we need to do our replacement reaction. So this lead, all right, first of all, nitrate's -1. There's 2 nitrates, that means this is overall is -2. That means your lead is +2. Your nitrate's -1. Potassium is in group 1A, so that's +1. And your iodine is in 7A, which is -1. First thing you should always do is check the charges. Make sure that you have your charges figured out for each element and ion. And so now we're going to take the replacement part. So the Pb goes to the iodine, So it forms PbI. Now, lead was +2. The iodine is -1. That means that you need 2 iodines. Now, we look at the second product. So potassium goes to NO3. Never carry the subscripts unless it's a polyatomic ion. So I'm going to bring over potassium, which is +1. I'm also going to bring over NO3, which is -1. I see that the +1 and -1 are going to cancel out, and so we're left with just KNO3. So we figured out our products. Now we got to figure out what is this precipitate here. So that's our question here. So to do this, we got to go back to the solubility rules. We got to look up the solubility rules. So for KNO3, we look up nitrate. We see that all nitrates are soluble. That means that this is aqueous. All right, easy. Now we look up the PbI2. So we find the I- on your solubility rules, and we look to see if there's any exceptions to it. There are 3: silver, mercury, and Pb +2. I come back down here and look, okay, so I got Pb, that is an exception, but make sure that its charge is +2. So I look back at the beginning, the charge of Pb is +2. So that means that this compound is insoluble. So it's going to be your precipitate here. So PbI2 is the precipitate. So this yellow compound that we see in solution here, that is PbI2. What I'll do is I want to keep this for right now. I want to add a new slide, and we are going to work on the next part. Now, please keep in mind that when we are working these types of problems, this is called reaction prediction. And reaction prediction is trying to predict the products from the reaction. So in the beginning of today, I talked to you about the 5 types of reactions. I gave you generic equations for at least 4 of them. So using those equations, they will help you into determining the products of the reaction. So now as we move into the details of a precipitation reaction, we will also need to work on how we write net ionic equations. So that's our goal right now, is to write out the net ionic equation. Now, what exactly is a net ionic equation? The easiest example I can give you is, if you go and work at a job and you get your paycheck, you look at your paycheck and you see that you made $2,000 on your paycheck. But then you go and you look in your bank account, you only have $1,200 deposited into the bank account. You're sitting like scratching your head like, what just happened to all my money? Where'd the $800 go? You got to remember, the $800 went to Uncle Sam. He took out your taxes. So what we're going to do is we're going to take out our taxes, and whatever's left over is going to be your net ionic equation. That's how I want you to look at this. So we're going to use the example that we worked with first, and that was the silver nitrate reacting with KCl to form silver chloride solid plus potassium nitrate. Now, the most important thing to remember here is which one is your precipitate, if you have one, and what is aqueous, okay? So if you are aqueous, all of your aqueous will be broken down into their ions. If you're a solid, it stays a solid. You do not break it down. It stays the same. So with that being the case, we look at our reaction. We see that we have 3 different compounds that are aqueous. Those 3 compounds are going to be broken down into their ions. We see that we have one solid. We don't touch that solid. So let's start with AgNO3. So Ag had a +1 charge, and it breaks down to these 2 compounds. Now, we look at the KCl. We see the KCl is aqueous, so it's going to break down in a similar fashion. All right, so here we have our 2 reactants that are broken down. We do not break a solid, so you keep it AgCl solid, but there is one product that we do need to break down, and that's potassium nitrate. So the potassium breaks down, and then your nitrate breaks down as well. So here we have our 2 products. So the next thing we're going to do is cancel out like terms. So which ones are your like terms, Devin? I pick on you because you've been talking to me all day. So which one are the like terms?
Do you mean like what's the A, B, the C, and the D sort of deal?
No, just look at it. And which one?
Oh, NO3.
Okay, all right. So I'm also
and potassium.
All right. So if everybody pays attention to that, you see that the potassium and the NO3 are the same on both sides. So what we do with those is we cancel them out. Now, these are your taxes, by the way. And your taxes in the terms here are called spectator ions. All right, so I'm going to box that in. So your spectator ions are your taxes. We take our taxes out. That's why we cancel them. We find out what's the same on both sides, cancel out the like terms, and then we bring down what's left over. So we bring down the silver, we bring down the chlorine, and then we bring down the AgCl. Now that is what's left over. That is called the net ionic equation. So we have our spectator ions here, and then we have our net ionic equation here. That is the 2 things that you are responsible for learning and figuring out in these types of reactions. Keep in mind, all this started with simply just doing AB plus CD yielding AD plus CB. It all started with that generic equation to where we get to the point where we figure out that that is our final reaction. So, any questions with that? All right, so I'm going to add a new slide here. And I'm going to try something. I haven't done this. I'm going to try this and just, so we're going to go to YouTube here, and I want to find my channel, and I think I have put a double replacement reaction on here. It would be somewhere. Here it is. Okay. So if you go and you look at this video, okay, I'm not going to watch this video right now, but I do examples after examples after examples with this. Now in the chat box here, I'm going to paste the link. All right, so there's the link. So y'all go ahead and open that link up in your Safari or whatever you're using to view Teams with. Go ahead and open that up. When we're done with today's lecture, I want you to watch that video, okay? I go into the same details, but the difference here is you actually get to see me teach in person. Is that I think I posted some general clips in here. Yeah, I don't see them, but I think they're there. I don't know, watch it all. And let me see here. Was there another double replacement? I think, yeah, here it is. So here is the net ionic equation. All right. And I'm going to go ahead and post this link in here. Yeah, here it is. So this talks about net ionic equation. All right. Let me go ahead and paste this in here. So you got two videos to watch. So watch the first one, which deals with just discussing double replacement reactions, and then watch the second one, which goes into net ionic equations. Everyone understand that and what you need to do?
Yeah.
All right. I'm going to be honest with you guys. When I made that second video, I had some students from the chemistry club make that video. I added music into it. I love the music. I think the music makes the best, makes the video what it is. So, but the student that you see doing the discussion, that's Maurice, and he is the president of SGA this year. So, if y'all are in SGA, you'll see him talking and stuff. So, are any of y'all in SGA, by the way, the Student Government Association? All right. Okay. Well, that's fine. If you're not, you're not. It's not a big deal. Okay. So let me go back to the PowerPoint here and all right, good. So I got my new slide up here. All right. So let's look at that other reaction before we move on to anything else. Okay. So PB NO3 plus KCl. Actually, it was KI. Yielded PB I2 solid plus K NO3. There's a 2 in front of that. Aqueous. Now, I'm going to show you a little shortcut here. This shortcut will help break down this a little bit faster. So if you look at KNO3, it's aqueous. If you look over here, potassium's aqueous. NO3 is aqueous. All right. Now, as we break this down, you're going to find that KNO3 ends up being your spectator ions. Okay. So you have PB 2 plus 2 NO3 minus plus K plus I. Need to put a 2 in front of that, by the way. Put a 2 there, put a 2 there. So very important, so that way they all cancel out. All right, and then we have 2 plus 2NO3 minus 1. All right, now what you see here is that the K's, potassiums, and the NO3s are the same, and so they're going to cancel out. So potassium and nitrate are spectator ions. All right, now carry down what's left over. So you have Pb 2 plus 2I minus. These are both are aqueous, yielding Pb I2, which is a solid. So this is your net ionic equation. So we have our spectator ions, and then we have our net ionic equation. So that's our goal, to figure out what your spectators are and figure out what your net ionic equation is. So the reason why we figure out the net ionic equation, so we can physically see what reaction's happening. So when we have two beakers being poured together into a main reaction vessel, what we're going to observe here is that you're going to have potassium ions, nitrate ions, and then on the very bottom, you're going to end up having your PbI2 solid. Precipitates do what? They fall out of solution. If you're not part of the solution, you are the precipitate. That's what I want you to remember. If you're not part of the solution, you're the precipitate. How do you figure out if you're the precipitate? You use the solubility rules. And that's a very important thing I want you to remember here, is that you always use the solubility rules. I'm going to give this one a 4-star. So don't forget to do that. I should give it a 5-star, just so that way it matches with what it's a 5-star rating, right? Don't forget your solubility rules. All right, cool. So that takes care of your precipitation. The next thing we're going to look at is your neutralization reaction, which neutralization is a whole lot easier, okay? So 2 is neutralization. Now neutralization is where you take an acid, react it with a base to form water plus a salt. That is your generic equation. Now this is still AB plus CD yielding AB plus CB. So AD, D isn't, it sounded like I said a B, but I said a D. So it's AD plus CB. Now, a good example would be HCl. Remember that your acids are on the things I should hand out, and then your bases, you're going to have to go talk about Megan Trainor for that. You're going to have to ask her. That was a terrible joke. Y'all don't know who Megan Trainor is, do you? It's all about that? Yep, you figured it out. Look at that, it's a base. So sodium hydroxide, I'm terrible today. I'm sorry. I have to do that every time I teach this. Now give it 10 years, nobody will know who Megan Trainor is. They're like, what the heck are you talking about? I don't know. Don't worry about it. It's all about the base. And we have rubidium hydroxide. We have cesium hydroxide. We have calcium hydroxide. We have strontium hydroxide. And we have barium hydroxide. What do you do with a dead chemist? You bury him. All right, so HCl is an acid reacting with sodium hydroxide. You're going to see a reaction like this here during the semester when we do titrations. And we did talk about titrations on Monday and I think last Friday, where we talked about solution stoichiometry. We didn't physically state it was a titration, but this is a titration problem here, okay? So HCl, so H is A, it's going to go to D, which is a hydroxide, and then the Na is going to go to Cl here. So you're going to form HOH. All right, so HOH is really supposed to be written as H2O plus NaCl. Now, using the solubility rules, you're going to find that NaCl is aqueous, it's soluble, but the physical state of water will never be aqueous. Water is pure, so water will be a liquid. Now, I want to make a little box over here that talks it. So pure liquids. There's two of them that you're going to work with. So water is one, and then bromine is the other one. All right. So these two are your pure liquids. Now you can do the same exact thing with this reaction as we did previously with precipitation. So H plus Cl minus plus Na plus OH minus yields H2O, because you cannot break a liquid down, plus Na plus Cl minus. Now what you'll observe here is the Cl and the Na are the same, so they'll be canceled out. So Na and Cl are your spectator ions. Then you carry what's left over down. So you have hydrogen plus hydroxide. Remember that what's in the parentheses here are AQ. So this is AQ, yields H2O liquid. So that's your net ionic equation. So just like we saw in the previous example, you still want to figure out your net ionic equation, and there it is. So for this reaction, the reaction that's happening is you're producing water. Now, the difference here is that you are not going to see a change in the solution, okay? So when you pour these solutions together, they're going to look the same. They're all going to have the same color, the same appearance. So to you, with your eyes, you're not going to see a change. But with the presence of your acid and base reacting together, they neutralize together. So when we talk about neutralization reaction, we actually can look at the pH scale. All right. So the pH scale ranges from 0 to 14, 7 being in the middle. Now 7 is neutral. 0 to 7 is acidic. So you're acidic. And then 7 to 14 is basic. So what happens is you take your sodium hydroxide, which is a basic compound, you react it with your HCl, and then they end up meeting in the middle at a pH of 7. Because the pH of water, pure water, is right at 7. That's why we call it neutralization, because you're neutralizing the acid and the base at the same time. Any questions on that? All right. So the last one, which is dealing with gas forming reactions. All right, gas forming reactions. So a good example here would be sodium. Let's see. So hydrogen carbonic acid reacting with sodium hydroxide. So this is aqueous. This is aqueous. Now, carbonic acid So this is an acid. This is a base. So you're going to produce salt plus water. So in this particular example, the hydrogen goes to the hydroxide, and then sodium goes to carbonate. So you're going to form sodium carbonate. Now I'm skipping over a couple pieces here, okay? The charges of sodium is +1, carbonate's -2. That's why I have a 2 as a subscript beside of sodium. That's why I did that. And then water is H2O. Now, in this example here, we have 2 hydrogens. So we're going to put a 2 here, and you're going to put a 2 here, and that balances the equation out. All right. So keep in mind, this is like your HOH. When you put a 2 there, that gives you 2 hydrogens. You put 2 because you have 2 hydrogens on the left, so you need 2 hydrogens on the right, but it also gives you 2 hydroxides, and that's why I put a 2 in front of the NaOH on the left-hand side. So the H2O is a liquid, and sodium carbonate is aqueous based off the solubility rules. All right, so we're going to cancel out the spectator ions, and I'm going to do this a little bit quicker because I don't have like 2 minutes left here. So sodium and carbonate are your spectator ions, okay? And so what you end up having is H plus 2 hydroxides yields 2 waters. So that would be your net ionic equation here. So this is your net. And then remember the spectators are sodium and carbonate.